Hey everybody, this is Larry. This is day 19 of 30-day Leetcode challenge. As you can see, I'm a couple of hours behind, but let's get right to it. I'm going to do this live and hit the like button, hit the subscribe button, hit the, I don't know, leave a comment. How do you think about this? How do you feel about this problem today? How did you do? Let me know if you have any questions, and here we go. Search in rotated sorted array. Suppose an array sorted in ascending order is rotated at some period unknown to you beforehand, and then you have some array. You're given a target value to search. If found is in the way, if found in the way, return its index. Otherwise, return -1. You may assume no duplicate exists in the array. Your algorithm one-time complexity should be on the order of O of log n. Okay. Yeah. So there may be a couple of ways to do it. I think. Yeah, I mean, I think when you see, well, first is when you see a binary, a log n complexity, and also, well, the first thing is if this was linear, obviously, is the solution's obvious. You just go through the way once, and then you search for the target, and that's O of n or of one extra space, sure. And that's, you know, that's so trivial of a problem that's not a problem, right? Like, that's just like, can you write a for loop? So that's probably not it. Even if they don't tell you the complexity, that's a little bit of the meta gaming, if you will. I think log n, immediately I think of a couple of things, which is either some sort of binary search or divide and conquer. I mean, now obviously binary search is an example of divide and conquer. Or just dividing. I don't know if this is conquering, but that's conquering. But yeah, so those are the kind of things that I would think about. And my two dots here is whether should I first try to find the first index in which it rotate over, or should I, and then after that you can just do a regular binary search, or should I just do it in one go? And I think that's kind of what I'm thinking about right now. Um, hmm. And I think they're both reasonable solutions. So I'm just trying to think about which one is easier to implement. And you could say that the first way of doing it, of just finding the period, yeah, that should be probably okay, because uh, yeah, because then you could cache that initial value, so that in theory, if you have multiple targets, then you don't have to keep on looking for the target and stuff like this. Where the divide and conquer one, maybe it's fine, but then yeah. But I think I'm going to do the divide and conquer because it's slightly easier to understand, maybe. But you can also I think the only other thing that I was going to think about was duplicate items, and it said that you may assume there's no duplicate items exist in the array, so that makes it easier to do. So let's kind of do that, and I think we can have a really simple recurrence as a result, right? Let's just go. Let's just go search the left index, right index, and target, and then let's just also set n is equal to the length of nums. That just make it slightly easier. Maybe I don't even know if I need that actually, but for now we can see if left is equal to right, that means we have one item. We might have to play around with off by, like, precise off by ones and stuff like this. But yeah, but then if nums of left is equal to target, well, we can just return this, right? If it's equal to that, then that is fine. And then now we have to figure out the divide and conquer recurrence. And then here we just take the middle item and then see if it's in the left or the right half, right? As simple as that. So middle is equal to left plus right divided by 2, and I know that there's a easier or a different way of writing this so that you don't, so that you avoid overflow. So something that keep in mind, but at least for now I'm not going to worry about it. Also, because if you're given 2 billion items, then well, that's a very tricky case, but it'll be okay, and it'll be interesting. But yeah, and of course you have to think about again off by ones and stuff like this, because you have, I don't know, say 3 and 4, this will always keep on returning 3. So, but yeah, but we just have to make sure we think about it. And I think we can actually make it slightly easier so we don't have to worry about off by 1, is that let's just actually change our base case, right? Let's say if right time minus left is less than 3, say, we can return target in nums of left to right. Yeah. And then that would be, does that kind of make sense? The idea is that for small constants, we just want the linear brute force. And in theory, this actually, I mean, okay, maybe not the way I write it because of the slice, but in theory, it gives great locality. And we could write it in a slightly different way. But because it creates great locality, because in a way, it's just going to be adjacent to each other. And so it's very efficient. And you could probably make some argument that 3 is smaller because a block size is like maybe multiples of 2 or powers of 2, and it'll be like 8 or something. And 8 inch is probably pretty good, or something like that. But that's something that you can have a chat with your interviewer as you're doing it. But yeah, but now we don't have to worry about this case about like off by 1s, because when it gets small enough, we'll just do a brute force thing anyway, right? But yeah, so now let's see if it's on the left half or the right half, right? So so now middle, let's say if, so middle is, so there are a couple of cases about the middle, right? And let's kind of illustrate this out a little bit. Okay, so middle is, if the middle is bigger than the left, then it's easy, right? So that's middle, sorry, the numbers of middle is bigger than the numbers of the left, then you know that it has to be either in the middle or sorry, it's in between the middle and the left or not, right? So yeah, so let's try that. If nums of middle, oh, this is actually return Boolean, so we have to actually clean this up. I forgot that we have to actually return the index and not the Boolean array. So let's actually change that to, yeah, I mean, we'll just write for index in nums or in range from left to right plus 1 so that we get right inclusive. And then if target is equal to num sub index, then we return index. Otherwise, we return -1, and we actually do it out here to be quick. Okay. So now, if num sub middle is greater than left, then we can do this thing where num sub left is, so if target is between these two numbers, and the less than equal is probably not necessary because all the numbers are duplicate, but actually no, it's necessary because target has to be one of the numbers, so never mind. So if that's the case, then we return search of left, middle, target. I mean, target is the same, so it doesn't change. And then if otherwise, then we search the other half, right? So let's return search middle, right, target. And actually, there is a little bit of off by 1 because we already know that target is not going to be equal to middle. So let's actually do middle plus 1. Yeah. Then now, yeah. And then the other case is if middle is greater than, I mean, I was going to say less than or equal to, but and that is the case when you have something like this, right? Let's just shift this a little bit by 1. Then this is, yeah, so this here, middle is going to be less than the left. So that means that it's contiguous on the right side, right? So now we can do a similar thing, but and we could inverse the logic if we want to be consistent from left to right, but I'm just going to do if nums of middle is less than target or less than equals to nums of right, and then in that case, let's just search, let's search middle, right, target. Otherwise, that's why, otherwise return search of left, middle -1, because again, it can't be middle, and then target. Yeah. And then that's pretty much all the cases. right? So now let's just return search of 0 and -1 and then target. And then let's give it a go. There are multiple cases. Okay, there are. And then we can play around with like the numbers as well. And let's change the case a little bit so that we did what we said before with the middle, and then again 0, 5, 4. And this is easy to test because, or in the sense that you know what the answers is from the inputs. So we're gonna take a look pretty quickly, and everyone looks match up. So let's submit it. Actually, let's try one more case with. Actually, no. I mean, we should, but in general, but in knowing my code, it's safe because I brute force on the left minus right is equal to 3. So yeah. Well, let's run it, and then now, yeah, it looks good. So let's submit it. Maybe there's some edge cases, but that's okay for learning purposes. But it's accepted. Yay! So yeah, so that's search in a rotated sorted array. Yeah. Okay. So let's take a look at the code. The code is, I think, actually, I try to be try to be a little bit better on the code quality. So I think this is good. And you can actually, I know that maybe they would the interviewer may ask for a perfect binary search, but or divide and conquer. But you can actually justify this really well, as I said before, with memory locality and and small indexes and stuff like that. So I think that's okay. And that will allow you to not worry about off by ones here. So I think this is actually relatively precise. You just have to keep track of the case where, like, for example, middle -1 is smaller than left or something like that, and that'll be false anyway. But but here I like to do something like this, at least especially during contests, so that I don't have to worry about the small ends. But that's up to you, of course. But yeah, so what is the algorithm? Well, every time we divide something by half, because we look at the middle, so it's going to be log n. Yeah, and that's pretty much it. And space is so space is a little bit tricky. So you can actually do this in O of 1 extra space, and we probably could rewrite this to be O of 1. I just wrote it in a way that makes it easier to understand. But you know, log n of for 2 to the 64 is 64, right? So O of 1 and O of log n space is not that big of a deal. But this is actually log n space the way I write it, because we put stuff on the stack, and the stack depth is going to be log n. So that you might have to be careful about. And actually, you could just change this to while loops. In this case, like here, you could do while right minus left is less than 3. And then here, you just set left is equal to left, middle is equal to, or sorry, right is equal to middle, and so forth. I mean, essentially, that's what you're doing, except for tail recursion. So in theory, you can maybe even optimize, or you could even make an algorithm that maybe compiler will optimize that, but maybe not, because it's very tail-y. As a recursion. But as an interviewer, this is an interesting problem, good problem to start off. Probably still a little bit on the easier side, but assuming that you already have binary search knowledge, or even not even binary search, just divide and conquer, right? This is given, and that's a very good pattern to kind of keep in mind, is that given a problem size n, can you break it down to a problem of size n minus 2? And when you could do that, then it becomes like n complexity, at least especially if it takes all of one step for each cost for each step. So yeah, so what else is there to say? Similar problems. Yeah, I mean, this is a divide and conquer problem. There's definitely a lot of similar problems. So I would think about just thinking about how to deal with these things. And it's a very, yeah, I mean, it's a very basic maybe even textbook problem, but I still definitely recommend it. So yeah, it's a very good problem and good for practice, good for learning. And yeah, that's all I have for today. Let me know what you think about the video, problem, or anything else in between. Leave a comment, leave a like, and I will see y'all tomorrow. Bye bye.